Hello and welcome to another video. In this video, we're going to be working on lexicographically smallest equivalent string. And in this one, you're given two strings of the same length, S1 and S2 in a base string. And they tell you that you have equivalent characters. So every pair of characters is equivalent and interchangeable. So here, like A and C are equivalent, B and D are equivalent, and C and E are equivalent as well. Okay, and because C and E are equivalent, it's kind of like a graph. So if these are equivalent, that means A and E are equivalent as well. So they tell you this, like A is equal to A. They tell you like what's the equivalence relation. So you have reflexivity, symmetry, and transitivity. And transitivity is kind of like the most important one. So here, because A is B and B is C, that means A is C. So they tell you like what you could build and what's the answer. So let's walk through this example. So in this first example, so P is equivalent to M, and then A is equivalent to O, and then R is equivalent to R. So every letter is already also obviously equivalent to itself, so I'm not going to write that. And then R is also equivalent to K. And I is equivalent to E. And R is equivalent to S. So here we can do it like this. So this is like this. And you can see like already a hint of this problem is you kind of have like connected components. So like this is a connected component, this is a connected component, this is a connected component, and so on. And then every letter that's not in here is just its own letter. So then when we look at the base string parser, we look in the group that P is in and we see like what's the smallest. So it's M. And then A is, there's nothing smaller than A, so we'll just use the A. R, smallest letter here is K, so we'll use K. S, smallest letter is K. I is E. And R is K again. So this is the answer. So essentially you can connect groups, and I'll talk about kind of two ways to do this. And let's go through this other example. So just get rid of this guy. So once again, held this hello world. So H and W are connected. E and O, L and R, and then L and L is already by itself, and then O and D. So here it's like this. So for this hold, H is the smallest letter, O is E or D, L is L, and D is D. So it's this HDLD. And then for the last one, so L is connected to P, E is connected to R, E is also connected to O, so we'll put an O over here. And then T is connected to G, none in here so far. C is connected to R, so we'll put a C over here. And then O is connected to A, so A. And then D and M are not in here, so D and M. And finally E and S, so there's an S here. So all of these characters, you're just going to want to pick A, and then these two, and so on. So for source, so S is A, O is A as well. U is not in here, so it'll have to be the U. R is A. C is A. E is A. C is A. O is A. And then D is D, and then E is A as well, I think. So it's this. So let's talk about kind of like the two ways you could do this, basically. So one way is kind of like you could do this union find because you're seeing like you're just connecting two letters, and then you could just see like in whatever connected component for that component, let's use the smallest letter. The other one is we can do it like a DFS, so actually going back, or BFS. So when we have this graph, what we could do is we can just say like, okay, let's take all of the keys of this graph. So essentially for every letter, we'll have like all the letters it's connected to. And then we can just build a map. So we'll take all the keys of the graph and we'll just build a map of like, okay, if we already traverse this letter, let's find the smallest letter in this whole thing. So what's that going to look like? So for example, for A, we're going to say like, what's A connected to? And A is connected to actually only O in this case. So we're going to traverse everything that A is connected to, which will give us all of this. And we'll set all of these equal to A as like the best letter. So A will be like A, C will be A, E will be A, R will be A, S will be A. And then we're going to go to the next letter, which is C, and we're going to say we've already looked at C, so we don't need to do that. Then for D, we're going to look at D, so D will be D, and M will be D as well once we do the BFS there. And then, so C, D, E, we've already done. F, G, so G and T, so G will be G, and T will be G as well. And then you just keep going like this, right? So you build this graph in the beginning from here, and then you traverse the keys, and then basically you just check like, have I already visited this component? And as you visit this component, you just find the smallest letter. And once you have this graph, then you just use this graph to get the actual output. Because basically you'll just say like, okay, L is in here with the letter of this and so on. But so union find is gonna be better here. And for one thing, note that like we only have 26 letters. So the number of like nodes is very small and the number of edges is very small. So instead, yeah, basically we're going to use union find, and we're going to make a small addition to, so you can kind of do the normal union find where basically you have like union find, you'll have some connections, you know, like A, E, O, M, whatever. Let's say this is a component and the parent happens to be M. And like normal union find, you're not guaranteed that the root of the thing is the smallest thing. So if M is like the root, you basically just going to find every component, and you'll get every single group that something is in. So let's say this is M is like number 3. So all of these will be number 3. And then you'll just say like, okay, for this group, what's the smallest? And then you can build that same dictionary like I was showing. So you can do a normal union find. But the better union find, and you don't have to do this, the normal one would be fine, just a little bit more code. The better union find is when we connect. Normally you connect union find based on rank to make like the trees as small as possible. But here there's only 26 letters, so even if we connect slightly inefficiently, like it's fine. So instead what we'll connect is we'll always make the root the smaller letter. So what's that going to look like? So let's walk through this example here. So for example, we're going to connect, first every node will be its own like parent. So we're going to have every single letter like A, B, C, and so on, and it'll be its own guy. But then we're going to take all of these. So we're going to say like, okay, let's connect L and P, and L is smaller. So we're going to actually say L is the parent of P. And then we want to connect E and R. So maybe I'll use uppercase to make it easier. So L and P. Now E and R, so E is smaller. So we're going to say E will be the parent of R. And then E and O. So E will be the parent of O. And we could still use the path compression, but we're not gonna like make the bigger tree the parent essentially. And then T and G, so G will be at the top. And then C and R, so C and R, so the parent of C is C and the parent of R is E, so actually it'll be like this. And then O and A, so O and A are the parent of O is C and the parent of A is A, so it'll be like this. And then D and M, so D and M are not in here, so D and M. And then E and S, so E is over here, the parent of, it'll be like this. And now whenever we want to get a letter, like let's say we want to get E, then we can just call find on the E and it will give us the best letter. So by connecting this way, like you notice that the root of every single tree is the best letter. So for this component, A will be the root. For this component, L will be the root, and this will be the root. So now all we have to do is just call find on every single letter. So we're going to make that small adjustment, and like I said, because these are only 26 characters long, even though we might not be making the small tree, like for example, we might have this big thing, and we're going to connect it inefficiently to a small letter. It doesn't really matter because it's only 26. So on these big graphs, like you need to use ranks to make it like true O of 1, but here, like because there's only 26 letters, we can just make this optimization. Alternatively, like I said, you can use ranks, and then for every group, find the smallest letter and just make a map of that. So it's like a little bit extra code. But yeah, either one's fine. So let's code up that thing I was saying. So what we're going to do is we're going to make a union method or union find method. And that's why it's important for union find to be able to make these optimizations. Like what if you need the number of components? What if you need this? What if you need this? It's important to know how to modify union find for like whatever you need. So I'm going to say private int array, and we're just going to normalize the letters A through Z. So this will be like roots, just like a normal union, but we won't have ranks anymore. And then we'll have the union find. size. And so basically we're just going to initialize every single one. So for, actually we need to make it first. So roots equals new int array. Technically you don't even have to pass in size because it's always going to be 26, but whatever. Okay, so 26, and then for int I equals 0, that's less than size. Parent I equals I. And yeah, we're going to use integers and just convert, or that's actually roots. So you can store as integers, you can store as characters. They're pretty convertible, right? So now we're going to have to find x, and this is just the cookie cutter find, nothing special here. So if roots x doesn't equals x, recurse find roots x. And return roots x. So standard find function. And now the and now we're going to write the union function, and then that one, like I said, we're going to connect in a different way. Yeah, that'll be fine. Void, we don't really need to care if it got connected or not. We can use void, we can use boolean, but we're just making the connections. So all right, so we're going to say like x equals find x, y equals find y. If the parents are equal, return. Otherwise, we're going to make the smaller one. So if x is less than y, then we'll make x the parent of y. Otherwise, go the other way to ensure that the parent is always the smaller node, and that's it. Okay, so now all we have to do is make this guy, so we can say union find equals new union find, and this is just 26 characters. So we're going to go through every single string in S, or we're basically just going to go through like the range of every single pair. So I equals 0, I is less than some length. So we're going to make a union between the two characters. So initially every character is its own root, but now we're going to make a union between all these. So union find union. And like I said, we don't need to know if it's true or false. So this will be character at I. And then because we're using integers, we need to actually do it this way to convert from integer to, or convert from character to integer. We can use characters as well, but I'll just do it this way. So essentially this will take the like normalized value. So A will be 0, B will be 1, C will be 2, and so on. So we're gonna make the union, and now we can build the result. And in Java, I guess you can use a string builder or like character array. I just use string builder, it's like the same thing. So now we can say, for this, you could do base string to character array, but that's more space, so we'll just go through it instead. Because right now our space is basically 26, so that's constant. Or yeah, I mean, you can argue constant, I guess. So we're gonna say int root equals union find. So we need to find this character. So base string character at I. We need to convert it to an integer. So that's the root of the character, and now we need to basically just convert the root from a number to a character. So we could say res append. So we need to convert it to a character in Java, and then we need to, so this is going to be like a 0 to 26. We need to convert it back to a letter. The way you do that is just root plus a to add back the ASCII value. So like 0 plus a will be a, 1 plus a will be b, and so on. And then we just return string. Okay. So I think, ooh, screwed up. Let's find out where. So it looks like we have P and M, and all the rest is correct. It's interesting. So yeah, I guess let's take a look at the code. Probably screwed up something somewhere. And union find character 1, base string. Okay. Roots I equals I. That's correct. So if x equals y. Oh yeah, so did it the wrong way. I mean, there's only a few places it can be wrong here. Okay. All right. And yeah, like I said, you can code union find, you can code graph. So graph, though, every letter can be connected to every other letter, I think, which would make it worse space complexity. Like here, you can argue constant, and I guess I will. So I'll just say like here, the time. So we'll say every union is still constant because, like I said, only 26. So I would argue like here, this is like string 1 plus string 2 plus string 3, and then space is constant, or like O of 26 or something. Yeah, so some important things for, so this is one modification you can make to union find. Make a union in a way you want to do it. Like I said, if these numbers were really big, I don't think you could do it this way, because then the ranks are important to actually append well and quickly. Although, I don't know if it matters too much if you still have the path compression. So, I mean, it'll be, yeah, I think it'll still be fine. But yeah, so some things you want to do is like that. Also, you might want to have like a connected components, also like a parent and some other stuff. So it's important to be able to modify these functions in a way to serve whatever you need. And so you want to understand like what union find does at a decent level to be able to do that. But yeah, that's going to be all for this one. Hopefully you liked it. If you did, please like the video and subscribe to the channel, and I'll see you in the next one. Thanks for watching.